And I see Sven is already online. Okay, so Sven, let me bring you in. Hello, Sven. How are you today?
I'm fine. Hi. I just needed to unmute myself. So
yeah, perfect. So, by the way, thank you again for being with us and our community at Zenoh User 24. So I see that you are already sharing your screen. So if you want to go full screen with your slides, I will. Okay, perfect. I will activate your screen sharing. And we are good to go. So once again, thank you, Sven. I will let you introduce yourself. And yeah, let's go.
Great. Yeah, thanks a lot for the opportunity and also the warm welcome to join here at the user meeting. I will talk a bit about how to put the Dragon, in this case Zenoh, into the car or the vehicle, because I've been involved in an activity called Eclipse Software-Defined Vehicle working group, so a working group down in the Eclipse Foundation or at the Eclipse Foundation. And there we have utilized a number of projects like Eclipse Kuksa and also Zenoh to build new blueprints. And that's the journey that I will take you on in the next couple of minutes here. Maybe to understand a bit more on the perspective that I'm coming from, let's do a classical who am I? So it was already introduced. I'm Sven Erik Jeroschewski, working with Bosch since 2018, and I started as a software engineer there, working on a lot of IoT topics. So I was quite used to all the very nice abstractions that you have made with Kubernetes and some other open source tools. Maybe you've heard about Eclipse Ditto in the past. And over the time, I also became involved in the Eclipse Kuksa project, which is over time a piece or a member in the Eclipse SDV working group, where I also worked with on behalf or with ETAs to bring some of these ideas on how to make application developments for vehicles more fun and efficient. And this is exactly what has driven me also in the past years in working on these open source communities. For instance, also becoming a committer in the Eclipse SDV blueprints. I will talk about what it is in a couple of minutes. So when we talk about SDV or automotive, so software-defined vehicle, there are a lot of definitions out there over the time. But I think what many people can agree on are some kind of promises. So we hope for very fast updates, having more like an app way of developing software compared to this classical firmware way of developing the vehicles, and this way also making it way faster to develop and also have reusable software. And since these promises cannot be achieved by a single vendor or a single entity, there's also huge effort in the open source community where people share the software-defined vehicle mindset, for instance, in the software-defined vehicle working group. So if you look into the project or the landscape there's multiple domains. So we talk about application development, we talk about orchestration and management of these applications, and also the runtime, so to run these things. And this is not just, as I just already mentioned, a single vendor activity. So we have a lot of strategic members. So there's BMW, Carriot from the Volkswagen Group, Mercedes-Benz, tech innovations, but also some classical tech companies like Microsoft or Red Hat as a participant member. So this is already quite a huge overview. So what I think is quite important is how to get data in and out. And this is out of the vehicle. And this is what we will talk about in the next minutes, and also where we heavily utilized Zenoh for. So that's the topic of the vehicle data abstraction. Because in automotive, as in many other industries, we have this overall problem we had this overall problem of a very high end-to-end complexity. So it was fairly possible to realize a certain use case for a certain model in a certain year, but it already becomes complicated if you change the model, or even more complicated if you change the model year. And we're still talking about the same brand. So this way, you ended up with a lot of data silos and very different data semantics, and also the complexity overall was quite high. And this is, I would say, a quite common pattern that you see in computer science, because you often end up in situations like this. And one approach here is abstraction. So the idea is to have some kind of vehicle abstraction to make the application development more scalable, to also decouple the applications from the actual underlying vehicle here, and also this way increase the portability and also reduce the maintenance efforts. Again, this is not a single entity or a single journey. So there's another open source project called Vehicle Signal Specification, or short VSS. So what VSS is doing, it's doing the structure of signals or data that you can find in a vehicle. So for instance, we can say vehicle.speed is the speed, and horn is active, describes the status of the vehicle horn. But we also add some semantics to it. So there's the description, there's also the unit and the types of being either a sensor or an actuator. And bringing this all together, we only have a data model so far. So there's only a tree of potential signals in this vehicle, but the question is, how do we actually interact with this data model? And one solution is the so-called Kuksa project. Because what Eclipse Kuksa is doing is, and now we read the slide from the bottom to the top, so it's a bit maybe counterintuitive. We start with the very deeply embedded layers, or ECUs, that you have in a car, like the control units. And there we only exchange data. So there's like, for instance, you could use CAN, and this has very specific signals. So only the very skilled engineers know that maybe CAN ID 62 is the speed, and this crazy bit mass inverted by 2 and something like this actually means the speed that we have. So this is the data. And this data then can be upgraded to information by aligning it or putting it into the VSS data tree. This is done in a software component that we call provider, because these providers take this domain knowledge and convert the data into the VSS format and then write it into a data broker. And this data broker and also some sample providers together are the Kuksa project. So that's what's also happening in open source, Apache 2.0 license written in Rust in the Eclipse Foundation. Having this data then in the data broker enables some of the applications or apps of higher function, like maybe an Android app or even an off-board cloud function, to consume this data from the data broker. And those create some knowledge out of the information that we got from VSS down from the providers and the deeply embedded layer. How does an actuation look like in Kuksa here? Because in a typical actuation scenario, for instance, here we want to open the trunk, we have some application that is setting a target value. So that's an important concept in the data broker. It knows the target value, and it also knows the current value. So by setting the target value in the data broker, we assume, again, some kind of providers which subscribe to these target values and are responsible and also ensure that this action is actually performed, or at least they try their best to do that. In this case, the trunk controller and hardware would then open the trunk, and we have another provider which is reacting to the trunk being opened and then setting the current value in the data broker. And this is exactly the second concept that the data broker manages. So besides the target or desired state of the vehicle, we also can see the current state of the vehicle. And here the application again would subscribe to this current state and then could visualize that the trunk actually has opened. So we have the whole control loop by setting the target, performing the actuation in the providers, and then reacting to the change of the current value. So this is really, in a nutshell, what we wanted to do with Kuksa here. And at some point, we decided, okay, it would be pretty cool to show this in action. So because if you only see the data broker as a piece in itself, it's a bit hard to explain and a bit hard to understand, okay, what is the value of this single component of this infrastructure? How do we actually create tangible use cases out of that? And this is a pretty good match with the idea of the Eclipse SDV Blueprints project, because the Eclipse SDV Blueprints project exactly tries to go for that. So a quote from the website: users can utilize blueprints as they are for inspiration or as a foundation to customize and meet their specific needs. So this way, the Eclipse Blueprints project becomes a collection of ideas in combination of Eclipse SDV and joint technologies to realize actual use cases. So we have a blueprint around ROS racers. There's a blueprint where we realize the same application. So to start a container, once you attach a trailer with different orchestration mechanisms, so different container orchestrations. There's also a blueprint to show how to interact with data spaces and share data from the vehicle with an external entity, in this case, insurances. And we wanted to have another blueprint showcasing how to use Kuksa. So what we ended up is a situation like this. So we had the data broker, we had some applications, for instance, an Android app. There's also an Android SDK for Kuksa available. But we really wanted to integrate some actual hardware, so some microcontrollers. So for a hackathon in the beginning of the year, we had an ESP32, which also makes it easier for people to reproduce this blueprint, because we obviously could have taken a classical automotive ECU and used some CAN bus, but this is not the typical technology available to the developers or maybe also university students that would interact with this blueprint. So we looked around and tried to put the Kuksa client SDK on this ESP, which did not work pretty well, to be honest, because we used gRPC and also HTTP2, which is a bit too large to be put in such a small device. So the question is, what do we put in here? And this is where we came across again Zenoh. So I think that's a really good match to connect the microcontroller for vehicle abstraction. You could theoretically maybe do it either only with Kuksa, but then you have some problems to put the whole Kuksa client on the microcontroller, or you even could think about only using Zenoh, but then you use some of the features around current and target values and also the native support of the VSS data structure. So what we ended up doing is we put Zenoh Pico in the microcontroller, which was way easier and worked pretty well out of the box. But then we still needed the connection with the data broker. And you can already see by this picture, there's still a missing piece. And this was the so-called Zenoh Kuksa provider, which we also have written to realize this use case or this blueprint. So what this provider is doing, it interconnects the API of Kuksa and the Zenoh network. And it actually was not too difficult when it came to the mapping, because we could simply use the VSS names as topics or as addresses in the Zenoh network. So this was quite easy to map. And then we still had the question, how do we differentiate between current and target? Because we could have maybe changed the signal name or the path name. But then we used another nice Zenoh feature, which is simply to write either current value or target value as attachment. So you can evaluate the attachment now to see whether this thing is, first of all, a VSS signal, and second, whether we talk about the current or target. And this code is now available in the Kuksa project, or to be more precise, in Kuksa incubation. So what have we achieved? We were able to set signals in the data broker, and these signals are now updating the microcontrollers. We also, that's maybe a quick other way to explain this, thought about writing a router plugin instead of having a standalone provider. But in our case, we thought it would be easier to deploy the provider as a standalone feature instead of having it always tied to the Zenoh router and also the build process being tied to the Zenoh router. That's why we decided, for the trade-off between this throughput and also the ease of development, to go for the slightly easier development and deployment by being or staying with the standalone provider. Still, as I just mentioned, what we have achieved with the signals, it can become fairly complex if you have more complex operations. So you end up quite quick in a situation like this, poor fellow and cans, because let's take a seat. In a seat, when you sit on that, you really care for your kneecaps. So you don't want the seat to go up first before going back. You want to go vice versa, so you should go back and then go up, because otherwise you will hurt your knees somewhere in the car. And this is one of the motivations for not only having signal-based approach in the vehicle, but also have services or introduce services. So there's a nice collection of services available also in Covisa called use services. And we decided to implement one of these services as an example, being the activate horn service. So here in the activate horn, you can send a whole sequence for the horn and play, for instance, a nice welcome sequence once the driver or the owner of the car approaches the car. And this is a bit easier in the abstraction, because instead of writing or setting the VSS signals every time for the specific sequence, you simply write the sequence and then the service is responsible for applying it. And this is exactly what the blueprint is about. So we came up with a new service to signal blueprint, which is now part of the Eclipse SDV Blueprints project. And here we have a horn client which calls this activate horn with our specific horn request. on the horn service. And this is done over U protocol with Zenoh as transport. I will not go into details what U protocol is, but it's a really nice abstraction for the service layer, and Pete will talk about it later in one of his talks. So what the horn service then is doing under the hood, it is using the set function of the data broker. And to this data broker, we have the Zenoh Kuksa provider, which is subscribed and is thus getting informed that the target value has been changed for the horn is active. And then we have again the Zenoh network, this time let's call it plain Zenoh, to put the value for the target value and as an attachment the target value under the specific topic being vehicle body horn is active. In this way, the ESP gets informed and can do whatever is necessary to actually honk or horn, or in our case, to still just activate an LED. So this is the way we implemented the blueprints for service to signal. As I've mentioned before, we also have other blueprints. So one striking example is the fleet management blueprint. So the idea here is you put yourself on the shoes of a fleet operator, like you can see on this picture, and you want to operate all these different trucks or commercial vehicles, and also want to ensure how they behave and what kind of data they have to process this in the backend. So initially we did something that, as you can see on the left, so we have an in-vehicle piece, which is assumed to be run on each vehicle, and we have an off-vehicle side, which is a cloud backend as a central backend for all these different vehicles. So what the vehicles are doing, they're sending the data based on VSS, or more specifically on VSS recordings, and send this data to a database in the backend. We used InfluxDB here. And in the initial case, we thought, okay, it would be good to simply go with the Influx API, but we had some concerns with this HTTP interface, sending the data over the air or cellular connection, and also some concerns regarding scalability. And this is where the team from some people from ZettaScale also came in and proposed and also implemented the addition of a Zenoh router. So now we have an alternative version of this blueprint using a Zenoh router instead of the direct HTTP connection. So you can see kind of a pattern here that we had quite some places in our blueprints where we were using initially HTTP or HTTP2, and then continue to replace those with Zenoh and the Zenoh router. And this already brings me to the end of what I wanted to share here, and also maybe with a call for action, because we're really looking for your ideas and also maybe further blueprints in the automotive domain, which either solve like a specific domain problem or also might be a good showcase for your technology, for instance, Zenoh. So thanks a lot again for having the opportunity to speak here, and hope to stay in contact.
Okay, thank you very much for the very nice talk. Actually, I have a question for you. Did you experiment, especially in the second last use case, when you were actually triggering the not this one, the previous one, the one on the horn? Yeah. Did you consider using queryballs?
Not fully, no.
Okay.
Could be an idea, yeah. Good idea.
Yeah. Okay, because that would be another nice way of mapping services over Zenoh. And again, the attachment use case was perfect, right, aligned with our intro. And I think something else worth pointing out is that attachment is not a single one, but it's really a map, right? So you can have a map of attachment, and it's a great way of expressing, among other things, higher level or higher protocol semantics piggybacked into the payload. So that's nice. So thank you very much for your presentation. Guys, are there any questions online? I know you guys are checking. So no. So, but if you don't mind checking the chat, because usually question comes with some delay, then yeah, that would be great. For the time being, thank you very much. Great presentation.